Part 1. The World of Aristotle. The ideas of the ancient Greek philosopher and polymath Aristotle dominated medieval European thinking. Aristotle taught that knowledge should begin with facts that seemed obvious, and then move step by step to conclusions. If all men are mortal, and Socrates is a man, then Socrates is mortal. He believed everything in nature had a goal. A tadpole aimed to become a frog. Fire aimed to rise. Aristotle believed the universe had 5 elements. Earth, water, air, and fire filled the world below the moon. A 5th element, ether, filled the heavens. He and other Greek scholars placed Earth at the center of the universe, and had the sun, moon, and planets orbit around Earth in perfect circles, a concept called geocentrism. Aristotle also claimed empty space could not exist. He claimed heavy objects fall faster than light ones, though he never tested this idea. Medieval scholars trusted his words more than their own eyes. Over time, universities and the Catholic Church treated Aristotle as the final authority. Many scholars believed ancient books already held all true knowledge, especially Aristotle's works and the Bible. But Europeans did not have all the ancient texts. In the 1300s, Italian scholars like Francis Petrarch, Giovanni Boccaccio, and Leonardo Bruni found and studied lost Greek and Roman works. These humanists wanted people to go back to the sources, ad fontes. Old Greek and Roman ideas could improve Christian faith and daily life. Artists and architects used these ideas to spark the Renaissance in Italy, slowly eroding blind trust in Aristotle. In 1440, Johannes Gutenberg invented the movable type printing press. Before this, monks copied each book by hand, which took a very long time. Most books used Latin, so only church leaders and nobles could read them. Printing allowed people to translate books into common languages and make many copies fast. A book that once took a year to copy can now be printed in a single day. By 1500, printing presses had spread across Italy, France, Spain, and England. These presses printed religious texts, law books, ancient classics, and proper stories. As a result, scholars stopped writing commentaries on Aristotle. They wrote textbooks organized by topic and included their own observations, encouraging new ideas and new systems of thought. The humanist idea of going back to the sources was expanded upon when Martin Luther began his Protestant revolt in 1517. He believed the church had corrupted true Christian teaching. He urged people to return to the original source, the Bible, and read it themselves to interpret God's will in their own way. This idea broke from Catholic practice, where priests controlled Bible reading and explained its meaning to others. Protestants began to read the Bible in a plain, direct way, without symbols or hidden meanings. They avoided church dogma that forced one interpretation. Soon, this direct style shaped how people studied nature. They stopped searching for secret signs and began to observe and describe the world as they saw it. People's ideas about the world kept growing after the Protestant Reformation. Starting in the late 1400s, Portuguese sailors began to sail down the west coast of Africa. The ancient Greeks had said the equator was too hot for people to live there, but the Portuguese explorers proved this wrong. They kept sailing and found a sea route to India, propelling their colonial empire to new heights. Spain wanted the same success. In 1492, Spain sent Christopher Columbus west across the Atlantic. He hoped to reach Asia, but he landed in the Caribbean instead. At that time, people did not have a clear word for what he had done. Writers used Latin words that meant find or explore, but before long, discovery took on a new meaning. It meant being the first to find something and opening it to others. People linked discoveries of all kinds to a clear date, a named person, a new name, and big changes in knowledge. Columbus died in 1506, still believing he had reached Asia. 2 years prior, another Italian navigator, Amerigo Vespucci, explored this land, and wrote back home that he had found a new world that was separate from Asia. In 1507, Martin Waldseemüller printed a map that showed these lands as a large, separate landmass bearing Amerigo's name. The discovery of the Americas demonstrated how real discovery could happen without needing ancient sources. Direct experience and observation would be the way forward. During the Renaissance, doctors followed ideas from ancient Greek and Arabic thinkers. They believed the body worked best when 4 qualities stayed in balance: hot, cold, wet, and dry. If these qualities fell out of balance, a person became sick. Doctors tried to restore balance to make the person well again. They also believed the body contained 4 fluids, called humors: blood, phlegm, yellow bile, and black bile, each tied to certain organs, symptoms, and the aforementioned qualities. These fluids had to stay balanced too. If doctors thought one humor was too strong, they tried to reduce it. For example, they often used bloodletting with leeches, because they believed it removed extra blood and helped the body regain balance. Many people also linked medicine to astrology and magic. They believed the sun, moon, and planets affected health and growth. Doctors looked at a person's horoscope to predict health, personality, and the best time for treatment. One key figure in this field was Paracelsus, a Swiss-German doctor and alchemist in the 1520s and 1530s. He rejected strict loyalty to ancient writers, and urged doctors to learn through experiment and direct study. He believed plants, herbs, and minerals held hidden powers that could cure disease. Paracelsus helped develop chemical medicine, mixing sharp insight with strange, esoteric beliefs. Other contemporary medical thinkers made progress in less mystical ways. Anatomy improved the most. Microservitus in Spain explained how blood moves through the lungs. Girolamo Francastoro said in 1546 that tiny particles pass disease from one person to another. He had no tools to prove this idea, but he strongly believed it. The most important contributor to 16th century anatomy was Andreas Vesalius. Born in Brussels in 1514, he admired Galen, an ancient physician who had shaped European understanding of medicine for centuries. In the 1530s, Vesalius translated Galen's Greek writings into Latin and added notes to explain them. In 1543, Vesalius published De Humani Corporis Fabrica, on the fabric of the human body. In this book, he described the ins and outs of the human body with many clear drawings in careful detail. Many people saw it as a high point of Renaissance understanding of anatomy. Vesalius corrected some of Galen's errors, since Galen had studied apes, not humans. Still, Vesalius kept most of Galen's main ideas. He focused on describing body parts, not on explaining how they worked. He taught students to dissect bodies themselves, which made anatomy more practical. His book spread widely thanks to the printing press, and influenced anatomy for decades. But on a larger scale, he and his Polish contemporary would change science forever. Part 2. The Copernican Revolution. Aristotle valued philosophy more than math. He believed philosophy explained why things happen and what they mean. Math, he claimed, only showed patterns. People used math in astronomy and music, but only to measure and describe, not to explain. Humanism changed this view. Plato had praised math as a path to clear truth. Now that more of his works were being uncovered, Renaissance scholars gave math more respect. In the 1400s, the German mathematician Regiomontanus argued that modern math and astronomy had fallen behind ancient learning. He taught that math began in Egypt, grew in Greece with geometry and trigonometry, passed to Arabic scholars who improved numerals, decimals, and algebra, and then returned to Europe in Latin texts. He saw astronomy as the highest form of math, and in his works he popularized the field. One key follower was Nicolas Copernicus. In the 1490s, he studied in Krakow, Poland, which had a strong astronomy program based on humanist learning. Around 1510, he wrote Commentariolis, and later developed his ideas in 1543's De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres. In it, Copernicus placed the Earth as a planet orbiting the Sun, an idea called heliocentrism, challenging the old geocentric idea that Earth was at the universe's center. Copernicus also claimed that the Earth moved, rotated, and was tilted on a revolving axis. He kept Ptolemy's perfectly circular orbits, but because his math was simpler and removed unnecessary assumptions, Copernicus felt that he was more correct. Many people misunderstood what Nicolas Copernicus meant in his book. An anonymous introduction, added without his permission, for he had died, claimed the book only aimed to help with calculations and did not show physical reality. This excuse made the idea of heliocentrism seem less dangerous. Most astronomers ignored Copernicus's deeper claims because it went against common sense and accepted science at the time, even though they respected his skill. Before the year 1600, only about 10 scholars trusted Copernicus's claims. One of them was Tycho Brahe in Denmark. Brahe wanted to know if math only described nature, or showed how it truly worked. Instead of agreeing wholly with Copernicus, Brahe created a mixed model of the solar system. In his system, the planets moved around the Sun, but the Sun moved around a still Earth. Many scholars in the early 1600s liked this model because it felt safer than a moving Earth, and more accurate than older ideas. People at the time believed the heavens were perfect as they were and never changed. Brahe showed that this belief was wrong by observing a new star, really a supernova, in 1572. He later studied comets and showed they traveled far out in space, not in the atmosphere as was thought. Medieval thinkers had believed planets were attached to invisible solid crystal spheres, carried through space by ether. If comets moved through planets' orbits, like Brahe observed, then these crystal spheres could not exist. As a result, scientists had to think of planets as objects moving freely through space. This raised a new problem. If not for spheres, what makes planets move. Johannes Kepler took on this challenge. He believed astronomers should explain how nature works, not just track where planets move. In his first book in 1596, The Cosmographic Mystery, he tried to explain the solar system using geometry. He used 5 special 3-dimensional shapes called platonic solids, where each shape has equal faces and angles. Kepler placed these shapes inside each other and fit the known planets in the gaps between them, almost matching real measurements of the orbits. His model also showed why people only knew 6 planets at the time. 5 shapes made 6 spaces. Kepler felt proud because his model made the universe seem ordered. To improve his work, Kepler joined Tycho Brahe in Prague to use his detailed data. Kepler supported Nicolas Copernicus, not Brahe's mixed system. In 1609's New Astronomy, he proved that planets move around the Sun in oval paths called ellipses, not perfect circles. He also showed that planets move faster when close to the Sun, and slower when farther away. We know these 2 ideas today as Kepler's first 2 laws of planetary motion. To explain this motion, Kepler used ideas from William Gilbert in his book De Magnet. Kepler suggested that the Sun exerted a force like magnetism to pull planets toward it. He did not say magnetism caused it, but used it as an example of the kind of force that might exist. Kepler's quest to show real causes, not just math, forced scientists to abandon archaic ideas and search for new explanations of space and motion. The next big astronomer to contribute to the field was Galileo Galilei, a bold and competitive man. He challenged famous scholars and refused to accept their ideas just because they held high status. Around 1590, Galileo attacked Aristotle, who said heavy objects fall faster than lighter ones. He believed objects moved toward their natural place at the center of the universe, which he thought sat at Earth's center. Galileo asked how fast objects fall, not why they fall. He argued that 2 objects made of the same material fall at the same speed, even if one weighs more. He built on ideas from Archimedes, who studied why objects float or sink by comparing their density to the material around them. Galileo treated air as the surrounding material. He said 2 iron balls, one big and one small, fall at the same speed because they had the same density. Galileo also supported Nicolas Copernicus. If Earth did not sit at the center of the universe, then Aristotle's explanation for falling objects collapsed. Copernican ideas also came from astronomy and math, not traditional physics, which suited Galileo's goals. In 1610, Galileo left the University of Padua in Italy and moved to Florence to work for the Grand Duke of Tuscany. This new job raised his rank and gave him more freedom. He no longer had to answer to professors who doubted math and science, as a powerful ruler now protected him. In 1609, Galileo heard about a new tool from the Netherlands called the telescope. He built his own and aimed it at the sky, changing how people view space. After acquiring the patronage of the Medici family, he found 4 moons circling Jupiter and renamed them the Medicean stars after them. But these were later renamed after Galileo himself. He then shared his telescopic observations in a short book called Sidereus Nuncius. He wrote that the Milky Way held countless small stars. He saw that the moon had mountains and rough land like Earth, and that light from Earth reflected onto its surface. In 1613, he studied dark, shifting spots on the Sun. Tycho Brahe said the heavens could change. Galileo proved that the heavens were alive. After this, Galileo continued to argue with other scholars, solidifying his ideas in 1632's Dialogue Concerning the Two Chief World Systems. The book, written in Italian and not Latin, openly supported Copernicus. Church leaders forced him to recant his words and kept him under house arrest because of it. In 1638, he published Discourse on Two New Sciences, a book that expanded upon his earlier work on motion and mechanics. Galileo later died in 1642. Though his career ended in restriction, his work reshaped science and astronomy forever. Part 3. The Scientific Method. Francis Bacon was born in England in 1561. Bacon believed knowledge should help improve health, comfort, and work in daily life. He asked Queen Elizabeth I to fund public gardens, libraries, and labs for useful research, but she refused. In 1581, Bacon joined Parliament. He tried to gain power, but struggled to rise, as older officials kept their posts for many years. Since politics blocked him, Bacon focused on changing how people studied nature. In 1620, he published Novum Organum. In this book, he criticized the old way of thinking based on Aristotle. He said people relied too much on debate and logic instead of real results. He proposed that scholars should gather facts, observe, test ideas, and remove wrong answers step by step. This method, called inductive reasoning or empiricism, built knowledge from experience. It shaped what people now call the scientific method. Bacon gave only one full example of how his method worked. He studied heat and gathered many cases where heat appeared, concluding that heat was a kind of motion. This idea matches modern science, which links heat to moving particles. However, Bacon did not believe matter had tiny particles, though his idea about heat remained unclear and raised new questions. Still, his focus on careful observation strongly influenced later thinkers. Francis Bacon's scientific method promoted experimentation instead of trusting old authority. Magnetism became one of the first big topics that used experimentation. Ancient writers had said little about magnets because they did not know about the compass, which helped new thinkers study magnets because they did not have to argue with old authorities. The compass also helped ships travel, so sailors and traders wanted to know how it worked. In England, William Gilbert made major advances. In 1600, he wrote De Magnet, on the magnet. Sailors had noticed that a compass needle does not point exactly north in every place. They also saw that the needle tilts up or down depending on where you stand on Earth. Gilbert studied these facts and decided that Earth itself acts like a huge magnet, explaining why compasses point northward. He also tried to link magnetism to Earth's motion, but he could not prove all of his ideas. Some Catholic scholars opposed Gilbert and his career, but thinkers like Kepler and Galileo valued his work and used it in their studies. Gilbert also worked with other experts who shared tools and results. They checked and added onto each other's work, making experiments seem more trustworthy. Whereas Andreas Vesalius aimed to expand upon Kane's work, the English physician William Harvey sought to correct him. Galen believed the heart stored blood, but did not pump it. He said veins and arteries formed two separate systems, where arteries carried heat and a vital spirit from the heart, while veins originated from the liver and transported food and nutrients to the body. Harvey studied medicine at the University of Padua and later became a doctor in London. He became a fellow of the College of Physicians and gave lectures that shared his ideas about the heart. In 1628, De Motu Cordis, on the motion of the heart, explaining how blood circulates through the body. Harvey showed that blood actually moves in a full circuit. The heart pumps it out through arteries, it spreads to the body, and veins carry it back to the heart via the lungs. He proved this with experiments on animals and careful observation. Harvey used social connections to make his ideas believable. He dedicated his book to King Charles I of England and Scotland, and the College of Physicians. The king's attention and the college's authority made it harder for critics to dismiss him. Harvey often performed experiments in front of respected witnesses, showing that what he claimed was real. Experimentation continued to go after other Aristotelian ideas leading into the mid-1600s, especially the idea that empty space, called a vacuum, could not exist. In 1643, Evangelista Torricelli used mercury in his tests. Torricelli filled a thin glass tube with mercury and placed its open end into a larger bowl of the liquid. The metal fell down the tube but stopped partway. An empty space formed at the top, which Torricelli said was caused by air pushing downwards. He died in 1647 before others confirmed his idea, so people spread news of his test slowly and often got it wrong. In France, Blaise Pascal tested the idea correctly. He asked his brother-in-law to carry a mercury barometer up the Puy-de-Dôme mountain. Pascal predicted the mercury would drop as he climbed. At the base, the mercury rose, and fell as expected when at the summit. This result showed that air pressure drops with altitude, and supported Torricelli's observation that air pressure, not a mysterious force, held up the mercury. However, whether or not the vacuum was truly empty, or contained tiny amounts of air, was still a bone of contention. In 1619, a French soldier named Rene Descartes was in Ulm, Germany, as war tore up the region. Stuck in the city, he had time to think. Descartes felt that human knowledge since the Renaissance felt messy and uncertain. He decided that knowledge, including science and philosophy, should be rebuilt from the ground up. He waited to publish his ideas after the Church condemned Galileo, though he finally released his major work, Discourse on the Method, in 1637. At the time, many people attacked Aristotle using skepticism. Skeptics said our senses can trick us, and that we can never feel fully certain. In his discourse, Descartes wanted to defeat skepticism by establishing certain final truths. He did so by doubting everything he could. He doubted his senses, math, and even the world itself. His doubts led him to one definite conclusion. The only thing he could not doubt was that he existed. I think, therefore I am. Descartes argued that the idea of perfection must come from a perfect being, which to him was God. A perfect God would not trick us about clear ideas, so clear ideas must be true. Using this rule, Descartes defined matter. He said matter only takes up space. Color, taste, and sound exist in the mind. The physical world determines size, shape, motion, and place. Descartes also claimed empty space and matter are the same. Empty space does not exist, because invisible matter, or ether, makes up all space in the universe. God made the first push to move matter, and the laws of motion, like gravity and magnetism, kept matter moving. When one part moved, it pushed another, creating circular motion, like whirlpools. He used these whirlpools, or vortices, to explain how planets move around the sun, and how objects fall. In Roman times, people used the word machine for large, strong structures like scaffolds or siege towers. They also used simple tools such as levers, pulleys, screws, wedges, and ramps. Galileo showed that machines cannot create extra force. For example, a light weight can lift a heavy one on a lever, but it must sit farther from the pivot point. This showed that machines followed the same rules as nature, but Galileo did not say that the universe itself was a machine. Instead, Galileo and many thinkers explained nature using tiny particles, an idea called atomism. They believed the size, shape, and collisions between atoms, or corpuscles as they were sometimes called, caused all physical effects. As mentioned before, Rene Descartes disagreed. To him, matter fills all space and moves like flowing water. Later writers grouped these sorts of views on how the universe worked under the name mechanical philosophy. Descartes said the universe works like a machine made of moving matter. He divided reality into two parts, matter and mind. Matter takes up space and follows physical rules. The mind thinks but does not take up space. The human body works like a machine, but can think because it has a mind. Animals, however, were more like complex machines, unable to reason or show emotion. After Descartes died in 1650, machines shaped new ideas. Inventors like Salomon Descartes built clocks, fountains, and organs powered by water, air, or weights. Their mechanical perfection inspiring people like Descartes to come up with his ideas. People also linked clocks and machines to ideas about how God, the universe, and motion interacted. Mechanical philosophy later influenced economic and social thought, where balance and self-correction in the market became important concepts. Part 4. I feign no hypotheses. During the 1600s, many pieces of art, architecture, and scientific experiments were paid for by the aristocracy and the monarchy. They used these works to show their power, prestige, and wealth. Many nobles also helped create scientific societies, academies, and colleges across Europe to foster further scientific development. In 1603, Federico Cesi began the Academies of Science in Rome. Galileo joined them in 1611. The group built a large library to help scholars compare ideas. Cesi's high social rank made people respect the Academy and trust its work. In 1657, Prince Leopoldo de' Medici founded the Accademia del Cimento in Florence. His brother, Grand Duke Fernando II, gave his support. The group had few rules, and only ran experiments when Leopoldo wanted. They collectively published all their findings in 1667, and disbanded soon after. Leopoldo's rank gave their work authority, and helped them avoid debate by focusing on results. While the Accademia del Salmento faded, two new scientific institutions took its place. In 1666, King Louis XIV founded France's Royal Academy of Sciences. Scientists were paid by the state to work in fields like astronomy, anatomy, mechanics, and chemistry, adding to the kingdom's power. Across the Channel in England, scholars formed the Royal Society of London. Compared to the Royal Academy of Sciences in France, they received little money from the state, and tried to stay neutral in politics and religion after England's civil wars in the mid-17th century. Inspired by Francis Bacon, they valued careful observation and useful knowledge, and their books carried great social and political weight. New science academies helped scientists work together. In 1645, Robert Boyle joined a small group that later became the aforementioned Royal Society. Boyle said scientists should report what they actually saw, not just guess. He wrote clear, detailed notes so others could judge the results for themselves. He also made sure trusted witnesses watched experiments to build honesty in science. Boyle avoided wild guesses, but he accepted the idea of unseen forces. He spoke of the spring of the air, describing how air can expand and push back. With an air pump built by Robert Hooke, he removed air from a glass container. He placed objects and substances inside, such as mercury, and watched what happened as the air left. When air pressure dropped, the mercury level fell, confirming Blaise Pascal's experiment. From tests like these, Boyle formed Boyle's law. If you squeeze out gas harder, it takes up less space, just as long as the temperature stays the same. After reading works by his contemporaries, Joachim Young in Germany and Pierre Gassendi in France, Boyle changed chemistry in a big way. In 1661's The Skeptical Chemist, Boyle rejected the ancient Greek idea of the four elements. He defined an element as a simple substance that cannot break down further, and can be used to form other, more complex substances. He also used chemical indicators to test how acidic or alkaline a liquid was. Boyle studied chemistry until he died in 1691 at age 64. The telescope let people see planets and stars in detail for the first time. Inspired by the telescope, the microscope uncovered a hidden, minuscule, yet equally as big universe. Some of the first microscopes were actually telescopes, as Galileo used his to try to look at nature up close. In 1676, Antoine van Leeuwenhoek in the Netherlands built a very small but powerful microscope. He used it to see single-celled life. He also saw tiny blood vessels called capillaries. William Harvey had predicted these vessels, but he could not prove they existed. In 1679, scientists saw sperm cells for the first time. Some observers believed tiny, fully formed humans lived inside sperm, while others thought they lived inside women's eggs. Because early microscopes were weak, some people believed they saw things that were not really there. Robert Hooke, an assistant of Robert Boyle, also helped microscopy grow. In 1665, he published Micrographia, the first great book on the microscopic world. He drew clear, detailed pictures of insects and other tiny creatures. His picture of a flea shocked readers, as they were surprised such a small bug could look so monstrous. Look showed that even a small louse had complex parts. The tiny world was rich, detailed, and full of structure. Even when scientists followed similar ideas, they often argued, as each person had different views. These debates sometimes led to new ideas, however, and the German thinker Gottfried Wilhelm Leibniz shaped many of them in the late 17th century. Leibniz strongly challenged Descartes. Descartes said the mind and body were separate, but if the mind thinks but has no physical parts, and the body has physical parts but cannot think, then how can the mind and body affect each other if they are so different? Leibniz gave a bold answer. He said God created a pre-established harmony. Mind and body do not directly affect each other. Instead, God set them up to match from the start. When you decide to kick a stone, your body moves and the stone rolls. Your thought and your action line up because God synced them up that way. In physics, Leibniz said force makes motion happen. He believed a passive force lets matter resist change, while an active force, or vis viva, gives matter power to act and move. Leibniz also said that when bodies collide, they compress and then spring back because they are elastic. Vis viva allows motion to pass from one body to another, or kinetic energy. Leibniz often argued with Isaac Newton in England. In 1665, the plague hit London, and Newton went to the countryside. There, he came up with the idea that motion was a combination of two parts: inertia, which keeps objects moving straight, and gravity, which pulls them inward. Isaac Newton wanted to know how gravity works. He studied how far a stone drops in 1 second. He then used Kepler's ideas about elliptical orbits and the inverse square law, and tried to calculate how far the moon should fall towards Earth each second. At first, his numbers did not match, so he set aside the problem for years. To fix this, Newton helped create calculus. This new math helped him study curves and moving objects. With it, he showed that a round body like Earth pulls on other objects as if all its mass sits at its center. Members of the Royal Society, such as Robert Hooke and Edmund Halley, then started to wonder how an object could move if gravity pulled it toward a body like Earth or the Sun. In 1684, Edmund Halley visited Newton to find an answer. Using his math, Newton said it would move in an ellipse, just as Kepler had shown. Halley urged him to publish his findings, which eventually became 1687's Principia Mathematica. In it, Newton added new ideas like attraction. Gravity makes every object pull on every other object. He also showed that comets follow oval or open curved paths as they move around Earth. Later, Halley used Newton's work to predict the return of a comet seen in 1531, 1607, 1682, and, as predicted, in 1758. Some critics, who followed Rene Descartes, disliked Newton's idea of gravity acting across empty space. They wanted a physical, mechanical cause, like vortices, even though Newton himself did not know exactly what caused gravity. Newton replied, "I feign no hypotheses." Newton's ideas spread at a slow pace. Principia Mathematica as a book was hard to read and very mathematical. Cartesian ideas were still popular, because teachers did not have clear books that explained Newton's system. Then, in 1697, Samuel Clarke added notes about Newton's ideas to a well-known Cartesian textbook. Over time, his notes grew longer and strongly criticized Cartesian views. Through these notes, universities began to teach Newton's ideas. By the 1700s, science had changed for good. Experimentation in the scientific method marked the decline of older ideas from antiquity, and when Voltaire explained Newton's work clearly to a wider audience, the final nails were hammered into the coffin. Scientists stopped asking what things truly are, instead asking how things act and how people can use that knowledge. They trusted careful observation, improved tools, and shared results with each other. Experiments helped them find new facts, even when they could not explain every cause. Francis Bacon pushed this change. He taught people to observe, test, and collect facts. He believed empiricism would help people understand nature and improve life. Descartes, meanwhile, doubted everything to rebuild knowledge from the ground up. He trusted reason to find certain, final truths in life. Newton brought these ideas together. He used math, experiments, and careful reasoning, refusing to make a guess without proof. His method taught people to study effects they could measure, even if causes stayed unknown. This approach built confidence in reason, and scholars began to apply the same methods to politics, history, and religion. They asked whether laws, cultural customs, and religious beliefs also needed evidence and reason. Before long, all of Europe would be enlightened to this new approach to learning.